have such good quality photos that they're always going to win. So, or at least push out some of the more novices, and we want them to have experience as well. That's why I added the youth category and the general category for people who just don't have as much equipment and experience. And as you can see, the quality of these images are quite good as well. Sorry about that. Let's see. So categories. So first of all, we have three divisions. The general division, which is the entry level, as I mentioned. Master class, which is for the advanced equipment and skill, and then the youth division for those under 25. And the general division and the master class each have three categories. I'll just sort of show you back here what that kind of looks like. So, so there's the solar system. So that's all solar system objects, of course, except for Earth. That's easy. And then we have the deep sky, which is deep sky objects. So anything, it doesn't have to fill the whole screen or fill the whole picture or anything, just anything with a deep sky object where it's the kind of focus of your picture. And last year we had nightscape, but we're just changing that to astroscape because there are the potential of taking pictures in the day with the moon and stuff. What we don't want is just like a holiday snapshot of the beach or the sun or anything, but something that's more astronomical of interest. But it can be day or night or evening or dusk or morning, whatever. And then the last category we have, did I say deep sky already? Did I do all three categories? Yes, I did. For the youth division, there's no three categories, there's just one. So everything will be sort of judged under that one. We have the judges lined up already, which is good. So the most important thing to know is the Tuesday, December the 20th is the due date for that. So that's the deadline for adding your submissions. That gives you another 52 or 3 days from now to plan any pictures you wished to have taken but haven't taken yet. So that would be great. Is there any questions? If there are, okay. Dennis?
No, that was just to agree when you said that anybody, at the very beginning, sorry.
Okay, gotcha.
I was just raising my hand, thanks.
No worries. Anybody else? Basically, all the information is on the website. We created a new email photo at mississauga.rasc.ca. So those will go to me. I will anonymize, just make sure when you submit your photos that each one contains the meta information we need, which is outlined in the PDF document. And you can send to photo@mississauga.rasc.ca where I'll anonymize them and send them off to the judges. The judging will take place probably next year in early January, February. And the prizes this year will be hopefully a nicely framed certificate with first, second, or honorable mention. So you can hang that on your wall for fame and prestige. And then of course, you'll be published on the website. But of course, we're just looking for people to have fun and partake because we want to promote astrophotography. So that's it for me.
Okay, great. Thank you very much. Any questions for Rob about that? So I assume that any pictures taken during the calendar year are can be submitted and
right, and it has to be your pictures too, of course, not something you found online.
oh, thank you, because there's some nice James Webb photos I was going to submit.
Yeah, I know.
Yeah.
Actually, I got one from Shaquille that I thought, wow, that's going to be perfect.
Yeah.
Yeah.
Yeah. Okay, I'm glad we pointed that out. All right, Rob, thanks very much. Yeah, great to see the contest up and running, and let's everyone submit the photos and look forward to to the end of the contest. So calendar year is the deadline, and we'll announce the contest winners next year, and we'll present the awards at the awards picnic in June. So something to look forward to there. Okay, thanks very much. Our next speaker is Ron Mcnaughton. Congratulations, Ron, RASC Service Award winner recently. So everyone clap for Ron for his contributions to the Society over the many years. And he's going to give a talk about James Webb. So it's in the news these days, and this was a talk he was going to talk about last month when or back when the pictures were first released, but that didn't work out. So he's going to talk to us about it now. And of course, there are a lot of new updates about James Webb, and of course the amazing new Neptune picture that released. So Ron, it's yours.
Thank you. Now, screen share.
Should be able to share. There you go. You're close. There you go.
All right. Oh, I thought I was at the beginning. No, I'm trying to close the. Okay, let me go back to the beginning. Anyway, thanks for letting me talk. July 12th was a meeting of another astronomy club I'm part of, the South Simcoe Amateur Astronomers, and I downloaded before the meeting every file I could find with max res of everything and did a brief unorganized presentation to that group. And then I put it into a PowerPoint, and this is what you get. I like to see the sense of scale of things, and this picture was taken a number of years ago, and probably most of these people have been replaced or whatever, but it just shows the incredible size of this thing that is at the L2 point. Discoveries include some of the spin-offs. Have they discovered things about optics that allow for better eye exam and more accurate results? And I know a few people that did laser surgery that have had problems, and it could be it will have positives, but the rest is astronomical. You all know that this is sitting at the L2 point, further away from the sun than the Earth, and the platform has a number of layers that cool it. This points to the Earth, so every month or so they have to stop observing and slightly change the direction that this thing goes. And of course, it originally was folded up, and the hundreds of processes, each one of which would have been a probably fatal flaw, failure point, all worked out, and it's just a stunning achievement to me for the group of which we were part that got it working. Anyway, light comes from, infrared radiation comes from far objects. It bounces off the primary mirror, goes up to the secondary mirror, and then nobody's really talked about what happens then. I'm going to. First of all, I'm going to talk about the primary mirror segments. They're about the size of a preteen, gold-coated, of course, and they can move them, they can tilt them, they can move them sideways as needed. And also they have points of attachment in the middle that can be tweaked to improve the figure to get the best possible optics. And I gather it's better than they thought it was going to be, so it's just been so stunning. This is the secondary mirror that's top of that tripod structure that goes above it, but it doesn't point directly to the center. So it goes into this structure here that has a name, but I'm not going to bother talking about it. So radiation comes, goes to the secondary, and then it actually goes a little bit to one side to the tertiary mirror. And this is a more detailed look. And the shape of this is so incredible because it's got to somehow eliminate all the errors, because this is a very low focal ratio lens or a mirror system, of course. And this shape is not a paraboloid, it's not an ellipsoid, it's some weird shape. And somehow they made it to send it to the steering mirror that is flat, completely flat, which isn't easy to make, and then it goes inward to a focal surface. Here's a model, and it shows there's a focus just above here, and it goes to the tertiary. This is where the steering mirror is, and then it goes down. Here's the tertiary concave mirror. I'm not quite sure what this person's supposed to do other than look pretty in the reflection. And like I say, that shape is unlike any standard shape of anything. And how they make it to that accuracy, I don't know. And I don't know if this could be used for maybe eventually manufacturers produce telescopes with a similar sort of design. So instead of a Dob that's, you have to be on top of a huge step ladder, maybe there's another way of doing it. I don't know. And this is a flat steering mirror that is controlled by one of our contributions, which is a fine guidance sensor. 16 times a second, it checks guide stars and it tweaks to within 6 milliarc seconds of accuracy. Now, if it's following a moving object like a comet, it's a little less accurate, but it's still pretty good. Now I want to talk a bit about the spectrum. Of course, the electromagnetic spectrum goes from gamma rays all the way to long radio. And I'm always going to talk about microns. So this ultraviolet here is 0.1 microns or 100 nanometers. And Hubble went from about 0.1 to 1.8. So it's band visible. Spitzer is middle to far infrared, and Herschel is all far infrared. And the last two ones worked well, but they needed cooling. And once the helium ran out, they were not very useful. And I don't understand why NASA didn't make a special spacecraft that could carry more helium to, say, Herschel in particular, which was at the L2 point. Now it's just orbiting the sun. I don't know why they didn't make a mission to be able to carry more helium and refill it, and then you get more years out of that good equipment that's up there at great expense, but they're smarter than I am. Anyway, oops, sorry, went too far. Webb, it's starts in the visible, I don't know, that's orange maybe, all the way up to 27 microns. So it's the near infrared and mid infrared, but it didn't go as far here. It was recommended by a decadal group of astronomers that do deep talk about what would be the most useful investments in astronomy for the next decade. And this was recommended in the year 2000, and it's only taken 22 years to get it up there, but it sure is worth it. Actually, Webb has two types of sensors that are pick up infrared from two different ranges. The near infrared is 0.6 to 5 microns. And anytime you see an acronym that's near something or other, it's the near infrared, and the near cam is, it takes the best pictures, and it's passively cooled to 40 Kelvin from all the sun shield structures that they've put up. The mid infrared goes from 5 to 27. And it's all in one instrument, MIRI mid-infrared instrument, and it needs further cooling to 7 Kelvin because these photons have less energy, there's more noise compared to the energy of the photons, so they have to cool it, and I'll get more into that later. Okay, here's NIRCam, and that is a filter wheel. And anytime someone applies to do research on this telescope, and every one of the projects that we saw on that first day were somebody's proposal, and it must have been a shock when they were suddenly told, you're going to get your results on July 12th, rather than having to wait a year for it. Obviously they went and they picked projects that would be visible when it was ready. Anyway, they have different filter wheels for the short wavelength channel and the long wavelength channel. And this one that I'm pointing the mouse, the cursor to, F150W, means it's centered on 1.5 microns, and it's wide. And in other places, there's a graph that shows specifically the range of wavelengths that are there. And I think most NIRCam pictures are made with 3 or maybe 4 different filters. So if it's a 12-hour exposure, it might be 3 hours of each one. I'm not sure, or 4 hours, I mean, of each one. I'm not sure of the details there. So here's the image that you've seen of the Planetary Nebula. And usually, but not always, they make the shortest wavelength to be blue and the longest wavelength to be red. So in this case, the blue is really what we would see naked eye red. All these colors are false. And the red is somewhere around 5 microns. I might point out a planetary nebula. It's sort of almost spherical, not perfectly. And it's sort of like this balloon. It's easy to look straight through and to see the belt buckle of the person holding it. But on the edge, even the thin balloon, it blocks the thing. And what we're seeing here is edge on, the edge. So that's what planetary nebulas are like. MIRI is a bigger instrument because everything is in it. The spectrograph and everything is part of MIRI. And now 5 is now the shortest wavelength and is blue, and 27 is now red. And it needs to be cooled. And the interesting thing about the cryo cooler is my refrigerator vibrates a little bit. Not that I feel it or bug it, but it does vibrate a little bit in the floor. And what they've got is a cooler, and they have 2 pistons that are exactly opposite, so they don't produce a vibration, because vibrations in space telescopes are not particularly a good idea. And there are 2 stages to this, and it's a whole story of how it works. So here's the MIRI image, and I'm going to compare the 2. Notice that NIRCam, which is the shorter wavelength, has diffraction spikes, but MIRI doesn't, because longer wavelengths bend around things a little bit better. Let's look at color. This red is 5 microns, but in the MIRI image, the same feature is now blue because it's now on the shorter wavelength side of the range rather than the long. So this red is also this blue, and maybe that's why they didn't want to paste them together. When you zoom in, remember I downloaded the full resolution versions of every photo I could find on July 12th, and haven't downloaded any others, by the way. Notice in the NIRCam, you get real details like good resolution. But in MIRI, with a longer wavelength, because things bend around objects a little bit better, you don't get the same resolution. And to get the same resolution in the longer wavelength, you would have to have a bigger telescope, or maybe there's some way, eventually they're going to find a way to make, say, 3 telescopes and put them 100 meters apart. And then you would get incredible resolution if they can work out the system of combining them just like they do now with radio waves, and that will happen eventually. And of course, you've got the fact that NIRCam shows 1 star and MIRI shows 2, but when I zoom in on the stars, the second star is there. It's partially covered by one of the diffraction spikes. But there's a pattern here I just want to explain. The bright star is about 100,000 degrees. That's part of its death part, and the sun will go through that. And that means it gives most of its radiation in the ultraviolet, some in the visible, and the amount given off declines as you go further and further into the infrared. So the star in infrared is a lot less bright than the star in near infrared. At the same time, the other star is often cooler, but I couldn't find the details of this, and I wish I could have. The other star is cooler, and it's going to give maybe more radiation at the infrared or the mid-infrared. So there might be 100-to-1 ratio of brightness here, and maybe 5-to-1 ratio here. And if they ever want to take a picture of an exoplanet without some occulting system, the far infrared produces a better balance of reduces the amount of radiation from the star, increases from the planet, and who knows if that will ever be done. Next is the Karina Nebula, and many people say this is the most visually appealing photo. It's not my favorite, but a number of friends said this is their favorite photo of the bunch. And given that it's in infrared, they can penetrate through the dust better and see specifically how stars form. So this was the NearCam plus MIRI image that I downloaded. So I trimmed the NearCam image that was on the previous slide. Notice the knob is missing. And you can compare that here. You penetrate through better to see more features underneath. And it said if you find a small red dot, then it's probably a star forming region. And what I did is I searched through this and I found this red dot that seemed the deepest red of anything. And that could be a star forming region. Who knows? When I heard Natalie Ouellette and somebody else talking about it, they were saying that this is that. As for this, I don't know what it is, but one possibility is that somebody left it cheesy on the telescope and nobody noticed it. I don't know. I just wonder. Comparing Hubble with Webb, you see how much more you can see through the dust because it's infrared and they can pick up many details. Anybody remember this album cover? It separated me from some of my money, and I didn't have an awful lot in those days. And it shows how also a prism can separate the colors. And I taught my students the acronym ROIGABIB for red, orange, yellow, green, blue, indigo, violet. This doesn't show any indigo, of course. And each one of these colors of the spectrum is a unique wavelength, and that's what our eyes can detect when we see color. It turns out the photon energy gets more when the wavelengths are short and less when the wavelength is long. Now, early cultures, for some reason, often would put some meat into a fire and burn it as a sacrifice for the deity or whatever it is. And the Bible has specific instructions in several places to soak the meat in brine. And it turns out every atom has certain fixed energy levels, is what quantum theory is all about. And one of the levels for the sodium atom is a drop from, you heat it and the electrons are pushed off. And then when they fall back, there's one transition that releases a yellow photon. So when you throw salt in any fire, you're going to get yellow flames. I have no idea if that's partially why the priests did that. Now, it turns out, and you're going to have to watch my picture here, and I don't know how this is going to work. Pretend my hands are a central atom and my elbows are outside atoms, so nothing is perfectly still. So the atom at ground state might have a little bit of wiggle. And then if something, or molecule, so if something gives extra energy to the molecule, it's going to be vibrating vigorously. But just like the atoms, the electrons in atoms are only fixed energy levels. Similarly, it can either be like this or like this or like this, but nothing in between. And when a molecule is stimulated and it falls down, it's going to release photons of specific energy. But also, if a photon of a specific energy goes through a gas with that, it's going to be absorbed at specific energies. And that's the reason why the spectrum of our atmosphere is so irregular. And it turns out infrared tells us about molecule transitions. I found this from NASA and tried to re-find it. This was in a talk about 20 years ago, but the atmospheres of Venus, Earth, and Mars have dips where there's a carbon dioxide evidence, but our atmosphere has an ozone O3. And given that it's 3 atoms, it's more likely to absorb certain frequencies or wavelengths, which is around 10 microns. And oxygen in the atmosphere is mostly O2, but there's a dynamic equilibrium where some of the O2s turn into O3s and O3s turn into O2s. And this is a bio signature that there's a lot of oxygen in the atmosphere, and there's huge research looking for biosignature gases on other planets. And one of the things they released is a transit light curve. And as this is a sun-like star, a little over 1,000 light years away, we could see it if it weren't so far south. I think this is never gets above our horizon. I'm not quite sure why, but most of the Webb was paid for by Northern Hemisphere countries, and the targets they picked were almost all Southern Hemisphere, except for Stephan's quintet. Anyway, you've got this planet plus an atmosphere, although it might be all atmosphere, but ends up being too thick. But the intensity of light declines by about 1.5%, which is 14,000 to 15,000 parts per million. But when it goes through, the thinner part of the atmosphere is going to block certain wavelengths of infrared light more than other wavelengths, because that corresponds to a particular energy transition of some molecules. So what they did is they did the spectrum of the star by itself, and then I think it's only one pass because they gave a specific time in Baltimore, not universal time, but I guess they have to appeal to American taxpayers. Anyway, they got evidence that there's clear evidence of water on that planet, and no surprise given that hydrogen and oxygen are number 1 and number 3 most common elements in the universe, if I understand correctly. So you get this, but I think that's from only one transit. But if you keep repeating this again and again and again, and every time a new transit comes up, every 3.5 days, they could point Webb at it for the short duration, and they get better and better details, and they can find out information about what molecules are in there. And it could be there's going to sometimes be a big announcement that NASA has found life elsewhere, or scientists have found life elsewhere. And it could be from finding a pattern of a biosignature gas or several in the atmosphere. And I understand there's a whole bunch of studies of the TRAPPIST, is it TRAPPIST-3 system, where there are a number of planets, and some of them have to be in the habitable zone. And I understand there's an awful lot of research going on there. Again, what you want to do is get many passes and average it to reduce the uncertainty. But it could be we have big news coming. Something like 1/3 of Webb time is monitoring exoplanets, but I couldn't confirm that. And I don't know if the Sarah Seeger star shade is going to end up being a place 20,000 kilometers away from this, from Webb, or from another, I don't know, but it's exciting times. My understanding, some of the big jobs at Starfest were not pointing at Stephan's quintet. Stephan saw 5 galaxies, but it turns out one of them is much closer. This is about 16 times the distance to Andromeda, and the others are around 120 times. So these 4, hello, I hear somebody's voice. These 4 are interacting with each other gravitationally, and this one is going there, and you have a shock wave with the interstellar or intergalactic medium or something or other. Anyway, the distances are found from redshift, where they look at the color, and this is a Hubble image, and you see the other 4 are less blue. And from redshift, that I'll talk a bit about later, you can do it now. I've given in million light years, but this is 92 megaparsecs. And for some reason, the Hubble constant is just this speed divided by that, and it's somewhere around 71. That's the current accepted value of the Hubble constant. Now, the NIRCam image, where notice that the different galaxies are relatively smooth, but you can see all sorts of interactions and long tails. Remember, this one is so much closer, so it's got nothing to do with the pattern of the other 4. But when you go to Miri, which is the longer wavelength, they're incredible detailed structures. And my guess is these could be star-forming regions that are cooler than the stars, so they get picked up at the longer wavelengths. And but I'm not sure. There's incredible detail here that comes out. Anyway, here's a combined image, and the scientists are just salivating at the detail that are in there, and I'm sure lots of people are madly preparing papers and everything. But this image is not only the galaxy, there are all sorts of other details in behind. And they're going to want to measure the velocity of different places, especially close to the central probable black holes of the different galaxies. So while they're at it, they want to measure a lot, and they're going to copy sort of a system used in the Sloan Digital Sky Survey. And what they do is they pick a certain patch of sky, and I presume take a picture of it. And then somebody goes through and picks out different objects of interest. And then they drill holes in this aluminum plate, and they put fiber optic cables in the different holes. And I have no idea how they know which fiber optic cable goes with which. Then they take a spectrum, but it has to be a long exposure because these, not much light gets through those tiny things, but they take long exposures and they get spectra of a whole bunch of things, and other scientists can pick areas. Webb has microshutters, and these can be shut, although there are a few that won't open and some that are stuck open, so they have to work around that. And what they do is they pick which objects are of interest. And this is 10 arc seconds. And here is a blow up of this area. And it's about 1.5 arc seconds across. So that's a pretty small area. And they can get the spectrum and various details. And here they've got argon ions, neon, and molecular hydrogen near a black hole, and they can work out the relative speeds of the gases and the distance. And from that, they can end up getting the mass of the black hole, how many million Earth or Sun solar masses. And my favorite image I left for last is the deep sky, and that's the one that Joe and Kamala got to see first, and it just blows me away. I think it was a longer exposure than the others. You see more deep galaxies than the others. They deliberately picked a spot where there was a big galaxy with huge mass, because what happens is you get these Einstein rings with the curves, and you can actually see some features that are more distant because the Einstein, can magnify it. When I gave my talk to another group, somebody asked me, can I explain Einstein rings? And I basically said, no. I find it a little complicated, but basically, just like the sun deflected certain stars a tiny bit when Eddington took a picture of during a solar eclipse to prove Einstein's general relativity was right, this is going to deflect light from a galaxy, and depending on how close the lineup is, you can get curves, but the same galaxy deflected by the same object can have a different radius of curvature. Like you'd think it would be the same, but that's all the geometry, and I'm sure there's incredible studies going on. Anyway, I looked at this, and remember I downloaded the full image, and I wanted to see some Einstein rings. So I thought this little patch here has 3 Einstein rings, and I'm going to look at them close up. So the next picture, I moved the picture down, and you're going to see that yellow area at the top. Okay, this is the same area in the same star. And this is an Einstein ring. And interesting, if you look here, this is the Einstein ring you can see, and it seems to continue up there. And apparently NASA took Doppler shifts of the Einstein ring in several places. I don't know if they also did around here, but would suspect they do. And it turns out this is definitely the same Einstein ring all the way around because it's the same distance away. My second Einstein ring doesn't look like an Einstein ring. And I have no idea what those dots are, whether they're globular clusters. Not quite sure why they're so bright. And my third Einstein ring, looks to me more like a spiral galaxy, but there's more on that coming up in a bit. I decided to paste the NIRCam plus MIRI image here with the MIRI only. I couldn't find a NIRCam only for this. And notice how the resolution is much less good on the MIRI only image. But I noticed that one of the deepest red things that I see in the long wavelength, so that's probably around 27 microns, is whatever that object is. And I don't know. I just find it rather interesting. And I'm just showing you for your enjoyment the larger scale image. And this is one of the deepest views that have ever been made of our universe. By the way, I noticed that this Einstein ring, it doesn't have a constant curvature, like it seems to be straight and then it bends a bit, and that could reflect the properties of the galaxy that it's deflected by. I don't know. I talked about Stephan's quintet and the Doppler shift speeds because in our universe, it's expanding and distant objects are generally moving away from us. And remember that these are 120 times the distance to Andromeda, and this is only 16. So what they did before, and this was published all the same day on July 12th, is they found various objects around in this deep sky image. They used the micro shutter to pick the different objects, and they must have done a long exposure. And this is way too small for you to see in the screen. So I'm going to take this part and you're going to see it enlarged in a sec. So if you take spectrum lines from rest, i.e. either you're observing something in a lab or you might be observing the sun because there's relatively little, the sun isn't moving away from us or towards us that fast. A little bit as we go from aphelion to perihelion, but not much. And you have various lines, and I took this from a source, and I think the hydrogen alpha should be a little closer to 6.5, but there's a hydrogen alpha line, there's an O3 line, a roughly half a micron, and then there's a hydrogen beta. Now, for the top galaxy in the picture I showed you, this wavelength that was a half a micron is now almost 2 microns. So it's expanded by, I don't know, 4, maybe 3.5, 3.8, but it's shifted, and every major line is shifted by the same multiple as you go across from the redshift. That's a property of it. So let's now look at the 4 models they had. So the O3 line went from a half to 1.8, so maybe 3.5 redshift. Actually, you subtract 1 because so it would be the redshift would be 2.8 or 2.9. Anyway, this one now it's gone to 3 microns, so it's gone from a half to 3, so it's a multiple of 6, or the Z value for redshift is actually -1, so it's going to be 5 and a bit. Here, with 13 billion years, it shifted even more to 4 and a bit. So it would be 8 or 9. The Z would be 8 or 9 because it's gone further. And the furthest one is 4, maybe close to 5. So it's got a redshift of 9 or 10 and 13.1 billion years. So we're talking about really old things. Then I thought, I actually want to look at the most distant object they found on this picture. So I went to the original massive massive file. I think it was something like 100 meg. And I found this area, and you see that galaxy there, which is there, and so on. And that's a star and some. And the reddest thing I could find is this. And I thought, no, it can't be that. It must be this. And that is the oldest thing that was found as of July the 12th, which is 13.1 billion years. And then when I looked at the diagram, yep, that's a 3. So I think since then, maybe more distant things have been found. But like I say, I've downloaded everything on July 12th, and I haven't downloaded any more images since then. So seeing back into the cosmos. You have your Big Bang, and HST, the Hubble Space Telescope, could go about 1 billion years. 1 billion years after the Big Bang, so 12.7 billion years. And they figured that the Webb so far on this one, it's 13.1, so it's about 600 million years or 0.6 billion years. And that's where the Webb so far is. And I've read that other people have supposedly found more distant things, but I'm not sure exactly what it is. But Webb is going to get to see maybe the first galaxies, maybe the first stars, if they get an Einstein ring where something really heavy is in between, it can magnify it. So we're talking about it. So we have a situation here where this lady's saying the James Webb Space Telescope is showing us images from 13 billion light years away. That's the beginning of the universe. Doesn't that make you ponder the very miracle of our existence? And the response is, we're out of beer. Anyway, thank you very much. If anybody has questions, I would be quite happy to answer. And I think I'm going to go to more astronomical, interesting slide. Okay.
Okay, thanks, Ron. Any questions? I don't see anything in the chat, but anyone want to?
I have a question.
Yeah.
I have a question. I heard that the MIRI instrument is not, there's a problem in one of the modes with the friction. Can you comment how serious, do you know how serious that problem is? Is it solvable, or is it like a sort of a game changer problem?
I must confess, I don't know anything about it, but I will definitely look up some information and make a comment on the our forum. Okay.
Yeah.
Okay. Yeah, it's a little early in the troubleshooting process, but I think they're going to work on it like they do other missions. So hopefully they'll be able to determine the characteristics of the issue and resolve. Any other questions?
Yeah, a great talk, Ron. I really enjoyed that. Just wondering, where do you get all of your information from? Mostly, because I imagine you're all over the place.
I enjoyed doing research. And most of the information came, obviously the files I just downloaded straight from NASA, but there is incredible documentation that goes with the Webb. I talked about the different filters, and then I said there's a place that gives the actual wavelength response for each filter, et cetera, et cetera. And they give incredible information on their site. And for other issues, I just do research. I often use Wikipedia, but I don't just read what Wikipedia says. They give references to other sources. And in many cases, I go to the other sources and look for information there to confirm or whatever. I deliberately decided I was going to stop at July the 12th. You know, there's no limit to the time I could have spent to research different aspects of this. So I just stopped on July 12th, and that's all you see. And I could see that somebody could put together an equally detailed talk of discoveries between July the 12th and now, because it's just continually flooding us with things like that Neptune image, and there was a Jupiter one. By the way, the telescope cannot take pictures straight away from the sun. The it can only rise so far from the platform of the thing, so they can't take any pictures of Mars, say at opposition, because then it would be straight away from the sun and the telescope won't do it. Anyway, any other questions? Thank you for listening.
Okay, thanks, Ron. I think I'd like to move on, but thanks very much for a really interesting talk.
Thank you.
Thank you.
And
Okay,
I'll, no, I have to stop share.
Okay, thank you. Our next speaker is David Maynard, who's going to talk about his experience at Point Pelee National Park. David, it's all yours.
Oh, sure. Make me follow such a great presentation.
You're welcome.
Alrighty. I'm just going to share my screen there. Can you see that?
I can see that.
Alrighty. So there we go.
Good.
Last week, my spouse Sandy and I got let out on good behavior, and we decided to try a little bit of glamping. So we went to Point Pelee National Park. And Point Pelee National Park is near Windsor. There's the Google map for that. And it is the southernmost point in Canada, the mainland point. There is Pelee Island and Middle Island a little further south. It's about a 3.5-hour drive for us from Brampton or Mississauga to get there. And of course, they made even longer by lots of construction on the 401. Seems to be eternal. It's either buried in snow or you can't drive around the pylons. So here's the park. The park itself is about 8 kilometers from the tip to the park gate. And it is being as far south as that it is, and to being pointing into the middle of Lake Erie, it is a totally different climate zone than what we have here. It is it's called a Carolinian forest. The forest there is very similar to what you would find in North Carolina. There's, through the park, we noticed when we were walking around, there's hardly any evergreen trees. There's very few conifers. Actually, I didn't see any conifers, and it's mostly deciduous trees, and it is heavily forested. So we stayed at this location here, Camp Henry, and the best observing place is up here at the Delorier Homestead. There's a big parking lot here, an open area. At our campsite, it was totally covered by a tree canopy, the camp tree canopy. And there is Sandy doing her best prices right. Here is our luxurious accommodation. And this is what they call an authentic. So it's hard walls and a soft top. And inside, it looks like that. And you've got ample sleeping areas, and it's all very nice and comfortable. And there's a big heater in there if it gets cold. And you can get it for $140, taxes all in, per night. So highly recommend it. So when we were there, we managed to catch the monarch butterflies in their migration. So everywhere I pointed my camera, I found one of these pretty little insects. So that made that part of was one of the valuable points of the trip. And when you're there, you do have to walk down to the tip. So there is the tip of Point Pelee, and you can't drive down there. You have to go to the main park museum and then take the tip tram, and then you walk the bit. So I discovered that walking a couple kilometers in sand really gives your calves a good workout. And here's a picture I took. As far as a place to go as a dark sky preserve, the sky is excellent for all directions except north. There is quite a light dome over from Leamington. So if you wanted to take a picture of anything that's close to circumpolar, you're not going to get great results. But from the east, the west, into the south, conditions are excellent. Now, the only way you can observe there is if you actually stay at the park, because they close the gate at 6 o'clock on weekdays and 9 o'clock on weeknights. So I was there with my camera and scope all set up in the parking lot, and the park warden comes in and says, "Park's closed, you have to leave." And I was like, "Excuse me, I'm staying here." And she was most apologetic for kicking up all the dust and from the gravel parking lot. So after that settled down, I managed to get this picture of the constellation Cygnus. And this is, I tried to do it so it was roughly like what you would see with your naked eye. So as you can see, the Milky Way is quite visible. And you can see here's Deneb and the wings and the Milky Way running right through it. So you could trace the Milky Way across the entire sky. So would I recommend going there? Absolutely. It's a gorgeous park, good facilities, like the washroom facilities, everything there at the campground was spotless. And it's a chance to see some dark sky and look at things. Most of the time I was just so thrilled by it. I just took out my my jumbo pockets sky atlas and just started identifying constellations that I couldn't see from Brampton. So take the trip, it's worth it. And that's anybody got any questions about the park? All right, here we go.
Robin has raised her hand. Robin has a question.
How busy does
Hi,
Hi.
David, that looks amazing. I was
Mhm.
just looking it up. They're open all year round. What's the heat source in those little tent things?
There, 3 of them have wood fireplaces if you want to be stuffing wood in it all night. But 8 of the 11 have propane or natural gas heaters in them. And it's actually, you know, we came prepared for fully camping, and we didn't even, there's dishes there, cutlery, there is a natural gas Napoleon barbecue right there. So basically all you need to do is your sleeping bags, your clothes, and what you're going to eat. Everything else is there.
Oh, that looks amazing.
Mhm.
Thank you.
Yeah, no, that's great.
David,
Yes.
it's Ron here.
Yeah.
Was there a light dome to the south, like the other side of Lake Erie? Cleveland is somewhere there, but maybe not due south. I'm not sure of the geography.
Yeah, directly south is Sandusky, Ohio, and that's the nearest part. But no, there was no light dome to the south. It was far enough away that it was pretty well dark right to the horizon. I would say this is probably a Bortle 3 to Bortle 4 sky.
David, a question from Kirby Alguire. Do people set up cameras and telescopes out on the point at night, or do they make you go to the open area gravel lot?
Well, you can't drive down to the point. They restrict driving down there. So unless you wanted to put your telescope on a wagon and haul it for a couple of kilometers, no.
Okay, great. No, it's super. Another great place to go for some dark skies, which is more and more of a challenge. So that's great. Any more questions from anybody for David?
I'll make a quick comment if I may, and I did just check this on the internet to make sure I wasn't hallucinating. Supposedly, it's the only place in Canada where you can see the Omega Centauri cluster, albeit you need absolutely perfect conditions. And I think it's only about 2 weekends of the year, sort of in late April, May. But it's a challenge object, I guess, for anybody who makes down to Point Pelee at that time of the year.
Yeah, well, there's you would have to, the view to the south was restricted by the forest there, so you would have to go probably to see it to go to one of the many beaches. Basically, the entire west coast of the point is one continuous beach, and you would have a clear view to the south. You'd have to do it when there's not a lot of moisture coming off the lake. So April would probably be good.
Certainly the time we were down there, if you want to see people with very expensive optics on their cameras, there's a huge number of bird watchers down there. and some really incredible camera setups. So nice to see people using fancy optics in the day as well as at night.
Oh yeah, I saw some pretty high-priced Canon telephoto lenses that are bigger than my 150 millimeter Maxitoff. Probably cost more than my house.
So you'd have to stand on a pretty high step ladder to see Omega Centauri, is that it?
Yes, but they do have they have a lookout, fairly high lookout that you can climb up to. It's kind of like a fire observation tower. It was closed when I was there, but it looks like a pretty substantial thing. So if you wanted to haul a portable scope up there, you'd probably be able to see it.
Great. All right, David, thank you very much for that that insight. That's I'm sure you've interested people in checking it out.
Well, it was great. My only disappointment about the trip down there was my cell phone still worked at the campsite.
Oh, okay. All right, thanks very much. We'll move on to our next speaker, which is Swapna Shrivastava, who is going to share with us her trip to Italy to seek out Signore Galileo. So Swapna, it's all yours.
Yeah, can you hear me and see my presentation? Okay, thank you.
Yes.
Yep. All right. So yeah, thanks very much for this opportunity. We had a great time in August, first family vacation since the pandemic began, a much needed one at that. So what I wanted to do is show you some images from our trip. And this was our first trip to Italy. The photos that you're going to see here are all taken by yours truly. And here we go. So I want to start off with Galileo. We all know who he is. But just as a quick recap, I wanted to share that Galileo was born in 1564 in Pisa. As a result of this trip, I actually did some research on him. I knew that he had invented a telescope. I knew about the Jupiter's moon discovery, etc. But I found out a few more things that I hadn't known previously. I didn't know, for example, that he was mathematics chair at the University of Pisa in 1589. I also didn't know that the Medicis, the famous Florentian family, supported his work. And then I was also very impressed and stunned by seeing his statue at the Uffizi Gallery in Florence. So that's the little picture that you see on the left. And on the right, you see the painting of Galileo at the Uffizi Gallery as well. And as I was researching, I got to know a little bit more about what he did for astronomy. So in 1609, he developed the telescope, which of course led him to the discovered Jupiter's 4 moons. He also studied Saturn and the phases of Venus. What I did know before this trip was that he was the first to discover sunspots. And in addition, he actually developed or improved several other scientific measurement instruments. In 1632, as you know, he published the famous Dialogue of the Two Chief World Systems in Italian. And that book compared the Copernican system, which is where the planets orbit the sun, to the Ptolemaic system, which is the Earth is the center of the universe, which got him into a huge amount of trouble with the Roman Catholic Church. And eventually, after many threats, Galileo had to recant his theories. And in 1638, Galileo went almost fully blind. And he died a broke man in January of 1642. So a great loss indeed. Very interestingly, it took the Vatican only 350 years to acknowledge Galileo was right all along. So that was in 1992. The next set of slides, this particular slide was very interesting. So this is from the museum, Museo Galileo in Florence. The first picture that you see here are the 2 original Galileo telescopes. That was so cool to see. And the bottom is the objective lens that Galileo used. It's said or believed that Galileo used these telescopes and this objective lens to find Jupiter. And so this was 1609, where he improved upon the original Holland spyglass to come up with the telescope. The reason the objective lens is framed is over the years, I think probably in the early 1700s, it actually cracked. And the Medici family had the objective lens framed to protect it. So that's in the museum. Another cool thing in the museum was a copy of the dialogue of the two chief world systems, which is what I just talked about, which was the comparison of the planets orbiting around the sun and the Earth, the center of the universe. In there, if you look closely, you see the sketches of the moon and some of his writing as well. So, you know, that was quite cool to see. I do hear some background noise, just FYI. And so what happened then is, as we're going through the museum, the coolest thing that we saw, and probably the most disturbing thing in the museum, was Galileo's middle finger. For those who've been there, probably not a surprise. I knew this was in the museum as I researched Florence and its sites, but when I got there, this was really, really cool to see. So for those who don't know why if this is the real finger, yes, indeed, the museum claims it is. And how they came about this finger was interesting. So back when Galileo passed in 1642, his body was actually buried in a private or unknown part of the Basilica Santa Croce. In 1737, when his work was acknowledged, and with the championing of the Medici family and others, his tomb was actually moved from his original location to this new location, which we'll see in a minute. During that move, one individual happened to remove 3 fingers, a vertebrae, and a tooth from his body. These items actually disappeared for about 100 odd years, and then came and surfaced again in the early 1900s, and eventually came into the possession of the museum less than 20 years ago. So there you have it. That's Galileo's middle finger. And the museum, I think, is in possession of most of these items that were originally stolen. So that was pretty cool and disturbing at the same time. So this is the Basilica Santa Croce in Florence on the left. I just wanted to show you a quick picture of the one I took. Inside, it is absolutely gorgeous. It is just stunning. And it houses some of the most famous Italian people, artists, historians, scientists, including Michelangelo, is buried at the Santa Croce. So some of the most famous Italians are buried there. And like I said, Galileo was buried in secrecy at the back, actually by the Medici chapel, the back of this particular basilica in 1642. And then he was relocated to this absolutely gorgeous tomb, which is across from Michelangelo's tomb at this basilica. So I paid close attention to this particular tomb and what was in it. So you'll see Galileo right in the center looking up at the heavens, and then he's got a telescope in hand and a globe with some books resting. Right below him, you'll see a circle. That little dot there is Jupiter with 4 other circles, which are Jupiter's moons. So this is a dedication to his work. To his right and our left is astronomy, and she's holding up a parchment with a sunspot right in the center. And on this side is geometry. So again, dedicating this tomb to everything that Galileo did and was interested in, and all of his contributions. So very impressive indeed. Let's go back to the Museo Galileo for a second. In the Museum of Galileo, I was actually surprised to see how many artifacts are dedicated to astronomy. There's more things out there in terms of measurements and precision instruments, etc. But these are a few other interesting objects I brought to this, I took pictures of really. So this one here, this globe, I'll start off with this globe to the very left, is a celestial globe by the medieval Islamic astronomers. And if upon close inspection, you can see the ecliptic, the celestial north and south poles, and several of our constellations. So you can barely make it out. It's behind glass, so I did the best I could to take that picture. In the middle is the famous Ptolemaic model of the universe where Earth is the center. So if you look closely, you see a bit of blue in the center. That's Earth. And all around it is the universe. This object takes up an entire room. It's massive. It takes up an entire room in the museum. And this is from the mid 1500s. Super impressive that it's still stunning, beautiful, and almost looks new when you look at it up close and personal. On the very right was a collection of telescopes that the museum has, anywhere from refractor to reflecting, mostly from the 18th century. It also has one of the first reflecting telescopes ever built. This was during the 18th century. And then as the time went by, you know, more and more small telescopes came into being, which of course we all know about. At the bottom, you'll see some very ornate wood-based telescopes that have developed over a number of years. So there's no shortage of astronomy-related objects in this museum for sure. Now I'm just going to step back and kind of go back out a little bit, and I want to take you through Rome and Vatican. So our trip was Rome, Vatican, Florence, and Venice, and some surrounding areas. So let me just show you some images from the rest of our trip now. So of course, we all recognize St. Peter's Basilica at the Vatican. The reason I'm showing this to you is because I want to show you a couple of astronomy-related pictures from there. This is the sunrise over Vatican. We had decided to take a very early tour so that we could get up close and personal with St. Peter's Basilica. And sure enough, there were just a handful of people at 8 a.m. in the morning in there. But as we were as we were waiting to get in, we saw the sun. And this is just taken from my iPhone. But I just thought, how beautiful that looked over the Vatican Square. And then the waning gibbous over Rome and the waning gibbous over Vatican City. So, you know, we you know, it's so much nicer when you're looking at it in person versus an iPhone. But again, something so pretty and, you know, kind of all coming together. And I want to talk a little bit about the Colosseum. There's no astronomy picture in there, but the reason I want to talk about the Colosseum a little bit is it used to be called the Flavian Amphitheater and was opened in 80 CE. And what I learned over there was the word arena, it actually means sand. And I didn't know that. And there's an underground where we went into the underground. We had a tour of the underground where the gladiators and animals were housed. And, you know, they had rope lifts where people would come out and do the shows. Of course, the beautiful Colosseum, which is almost 2,000 years old, is an engineering marvel and has existed despite earthquakes. Many of its parts were taken away to build other monuments in Rome. So a very, you know, limited facade still remains, but still very impressive. If you haven't been there already, I do encourage a visit. It'll be worth your time. Now let's move on to Pompeii. For those who know me, I've been around. I like volcanoes. So of course, a trip to Pompeii from Rome was important. So what we did is we got on a train. The trains in Italy are just fantastic. They're the high-speed trains that move at 300 kilometers an hour. I wish Canada had one of those. And we made our way to Naples. I had connected with an archaeologist, a working archaeologist at Pompeii before I left. And she met us in Naples and gave us a private tour. She picked us up in Naples and then took us to Pompeii and spent a half a day with us at Pompeii and even fed us some ice from gelato along the way. So I want to share a few things that we saw there. Nothing astronomy related, but just history in here is just absolutely fantastic. The city of Pompeii, of course, is very, very famous. It was destroyed by the Mons Vesuvius eruption in 79 CE, which covered, you know, about 19 feet. 19 feet of ash covered that city. So beautifully preserved ruins. About 90% of these residents escaped, but many still died. What I didn't know was it was the biggest archaeological dig in Europe, and it's still an active excavation site. So here's the archaeologist. She's in blue. She actually, we're standing here. This is the spot she and her professor discovered. This is a house from 79 CE that she and her professor discovered. So how cool is that? What I learned over there is that they like to eat out. The Pompeii folks wanted to eat out. They ate from street corners. They liked soup and wine. And here are the bodies of Pompeii. I'd only seen them in pictures, but we got up and close and personal with this. So in the center, it's a woman who was actually covered in ash and pretty much died instantaneously. And her body was recovered. Like about 1,000 bodies have been recovered from the Pompeii area. On the top right are remains of 7 men who came after the volcano had erupted and tried to rob Pompeii. Unfortunately, they weren't successful, and we find them here. Behind them is a couple of walls, which are the original frescoes or paintings. You see the little bit of red and yellow from you know, almost 2,000 years ago, still well preserved because of the volcanic ash. Now let's move on to Venice, some pictures from there. So back to astronomy for a second. So here we have the bell tower. For anybody who's been to Venice, you recognize this as the St. Mark's Campanile. And this is right by the very famous St. Mark's Basilica and by the Doge's Palace. What I learned as part of the research that I did on Italy was in 1609, Galileo demonstrated his telescope to the nobles and the Doge at this particular tower. And it, in fact, was very well accepted. So that's the tower. Unfortunately, we couldn't go up. This is a sunset over Burano Island. I'll speak to Burano Island in a minute. But again, you know, an iPhone can do only so much, but the spectacular view of our sun over another part of the world it's a must-have to capture. And yet another one is Jupiter. This view, and it's very, very tiny because the lights are quite bright around here, but that little Jupiter is right there. That little dot there, not little Jupiter, but the little dot there is Jupiter. And this was, we had come back from a very long day and we stopped in front of our hotel and we saw Jupiter right in the sky. And of course I had to click. So here we are, and what a view, we thought. And have some other fun facts, non-astronomy related, but fun nevertheless. So this is a view from the Bridge of Sighs of the Doge's Palace. What I didn't know was Casanova was actually imprisoned in these prisons of the Doge's Palace. And the view you're seeing here is as if a prisoner was looking out. And the reason it's named the Bridge of Sighs is because when the prisoner looked out, this was their last time they could see Venice and the beauty, and the prisoner sighed. And therefore the Bridge of Sighs. This statue is at the Uffizi Gallery, actually right next to Galileo's statue, the statue of the Amerigo Vespucci. I did not know that that America is actually named after this individual. Amerigo Vespucci was actually an Italian merchant, explorer, and navigator. He's buried with Bocelli in Florence, in a basilica that near the hotel that we were staying at. I don't have pictures of that, but I just thought that was very interesting. Bocelli, of course, the famous painter who did the Venus painting. And this is Banksy Art in Venice. So my daughter Isha actually researched this, and she made sure that we got to this art. You'll see that this building, you'll see this little person, and then you got the pink kind of smoke coming out of it. That's Banksy Art. And as a result of rising water, that art is actually vanishing, you know, pretty quickly. We did notice that many buildings in Venice were quite run down and boarded up, similar to the one that you see here. But how cool was that? I've never seen Banksy Art before, but how cool is that to just come across it? Thanks to my daughter, we found it. And this particular tomb is of Margherita, the Queen Consort of Umberto I. So if you like Margherita pizza, it's named after her. The pizza was invented in Naples, and that store that was this restaurant that was invented it is still around. Unfortunately, we couldn't go because of a variety of reasons. However, she inspired the invention of the margherita pizza, and therefore you see the 3 Italian colors, white, green, and red, and they're from the flag of Italy. This particular tomb is in the Rome Pantheon, in the Pantheon in Rome. And how cool was it to see an unfinished sketch of Michelangelo at the St. Croce, Florence? So obviously he started on another masterpiece, but he couldn't quite finish it. But somebody found the unfinished sketches, which is pretty cool. So just a quick round table of what else? The final images from Italy. So I mentioned, I'll come back to Burano Island. Spectacular. Look at the colors, and the sky was just blue, hot, but beautiful blue sky. Burano is the fisherman's village. It's about a 30-minute boat ride on the Vaporate, which is the commuter boats that run, pretty much 24/7 in Venice. So it's a 30-minute boat ride from Venice to the Burano Island. It costs about €7 for the day, which is €7 per trip, and which is pretty cool. And this island is known for lace making. The reason the buildings are so colored is because they would want the fishermen would be able to find their houses easily at the end of the day. So each house is painted of a unique color. Were they all unique? I'm not so sure, because I see a couple of oranges already and a couple of pinks in that picture, but beautiful. Of course, Florence has so much history, the heart of the Renaissance and the heart of the start of, coming out of the Dark Ages for Western Europe. So beautiful. Venice, of course, this is a view from the famous Rialto Bridge, very busy waterway. I've never seen a city like it. It's got no vehicular traffic, just boats. Even Amazon deliveries were happening on these boats. Big crates of water and food were all being boated in, and it will seem like clockwork. They knew what they were doing. Never seen anything like it. So beautiful. And the Castle Sant'Angelo, which is the mausoleum of the Hadrian. This is connected to the Vatican. Our hotel was very close to the Vatican, and we actually were able to walk to this particular castle. It's again super old. Couldn't get in, but I just thought of course the sun rays hitting the castle looked really nice, and that's why I included this particular picture in the presentation today. So that's our trip to Italy. Thank you very much.
Thank you very much, Swapna. Any questions? That was a great visit. I feel like we were back in Italy there.
Randy, I just wonder if there's any relationship between Galileo's sunspot observations and his later blindness.
Okay. Maybe. If you look through the telescope, I guess.
Actually, I can speak to that.
Okay.
Yeah. Apparently, they knew better, and they knew that they couldn't look at the sun directly. So no, the answer is no.
Okay.
And the Italians are well known for their development of welder's glass. So.
Okay then.
Just a little tidbit. Any other questions for Swapna?
Swapna, do they allow pictures in the Galileo Museum? Because when we were there years ago, pictures were not allowed, and yet you got pictures of his finger and his telescopes. It was surprising to see that.
Yeah, yes, pictures were allowed. And in fact, all the pictures you saw are I took them. And in fact, I've got, I think just from the Italy tip, I have 700 pictures, and a lot of them are from that museum. And so, yeah, there was no issue. In fact, we took multiple, we stood by it too, and just going around, there was no issues whatsoever.
Okay.
This isn't so much a question. Galileo had a daughter, and she was sequestered into a nunnery, because you heard about that. There's a book called Galileo's Daughters. It's about all the letters they wrote back and forth. And it's kind of a shame, because she probably could have been equivalent to him if she was allowed to be, if you know what I mean. But of course, the times being what they were, as soon as his wife died, it was no longer considered acceptable for him to have the daughter at home with him by himself. So he had to put her into the nunnery, a thing which he really didn't like to do. And he kept giving her money and stuff. But if you read Galileo's Daughter, it's a fantastic book and a very good insight into some of his personal life and her personal life too. Did you come across that in the museum at all, Swapna?
No, not that I've seen. In fact, during the research, doing this presentation, I did read about his daughter, but I did not know there was a book by Galileo named Galileo's Daughter. And no, I did not, at least I didn't see any references to his
Okay.
daughter.
I recommend it. It's a good read.
No, I will look it up on, see if I can get my hands on one.
Great.
And Kirby mentions in the chat, he's posted a picture of a plaque at the top of the tower in Venice where Galileo demonstrated his telescope. So going to the chat, Kirby's got a picture there.
Yeah, Swapna, it sounded like maybe you weren't allowed, maybe they had it closed that day and you weren't able to go up to the top of the tower. But if you do, by the window where they think he did the demonstration, there's a kind of a painting of him demonstrating to a few dignitaries, including the Doge, and then there's that plaque. I don't know Italian, but it's about that event.
Oh, cool. Yeah, I had heard about it, but yeah, unfortunately we couldn't go out. Yeah, thank you very much for that. I will take a look. Thank you.
I'll just say that it's interesting that the book that Rob mentioned, I think, is by the same author, Sobel, that wrote Latitude, which a lot of us really enjoyed, or Longitude.
Longitude.
Yeah. Longitude, yeah. So I'm going to look into it. Thanks, Rob.
Welcome. I just posted it in the chat, link to it.
Great, thank you.
You'll probably get it anywhere. Yeah.
Excellent. Thank you very much. Thanks again, Swapna. Super.
Thank you.
I'd like to move on to our last presentation, Rick Veregin, and it's a astrophotography presentation using a narrowband filter. Rick, are you with us?
I am.
There he is. It's all yours.
Let's see. Can you hear me and see me?
I can hear you. I can see your presentation.
Okay, great. So I'm going to talk more about my experiments in astrophotography and light polluted skies using L Extreme versus an L enhanced filter. So I hope people aren't tired of hearing about my never-ending experiments with my fight on light pollution. So just very briefly to remind you about my equipment, I have a Celestron C925 Schmidt-Cassegrain telescope. So it's 9.25 inches of aperture, and I use a reducer, so it's f6.3. And I have a ZWO 2600 MC color APS-C cooled astro camera. And the rest of the information here is for reference. So, you know, I've over the years of trying to take photographs in the light polluted skies that I'm under in Mississauga, I realized with Bortle 8, the light pollution really demands a narrowband filter if you really want to take good images. So I've talked before about the filter here, which I'm showing on the bottom. I'm showing the transmission versus wavelength of the Optolong L enhanced filter. It's a 2-inch filter, which is about $300. And recently I purchased the L Extreme filter, also from Optolong. Again, it's a 2-inch filter. This one's a bit more pricey. It's $380. Now, both filters are quite similar. They both pass O3 and hydrogen alpha. The big difference is if you look at the L enhance, the half bandwidth, full with half maximum, sorry, it's plus or minus 12 nanometers. So for O3 for the L enhance, whereas for the L extreme, it's plus or minus 3.5 nanometers. So quite a bit narrower. And for H alpha, it's plus minus 5 nanometers for the L enhance and plus 3.5 nanometers for the L extreme. So because of the narrower bandwidth, if you think about it, the only light we're letting in is in that very narrow band. So if the band is narrower, we're letting in proportionally less light. So my own calculations for light pollution, I found my L enhance reduces the light pollution by about 13 times. So that's pretty significant. And then I did a quick calculation just looking at the bandwidths and saying, well, if we get proportionally less light coming through in those bands, we should get about 2.5 times less. So compared to no filter, we're down to about 1/33 of the amount of light pollution. So it's a really huge improvement with both of these filters, obviously. The other interesting thing is because the L extreme is much narrower for the O3, it blocks out hydrogen beta. Hydrogen beta line is quite close to the O3 line. And so as a result, while the L enhanced lets in the hydrogen beta totally, the L extreme blocks it totally. So it's a little bit cleaner signal from O3 with the L extreme by blocking out that hydrogen beta signal. Okay, so, I've been only showing like 30-hour images and so on in the past. I want to show you something that was a little bit less time. So these two images are pretty much raw data, just stretched a little bit and color processed to color balance a bit. So on the top is the L extreme, on the bottom the L enhance. And again, this is in Bortle 8 with 11-minute exposures. I was pretty, pretty impressed by what you can get with just a very short exposure. And, you can pretty these up a fair amount too, if you want to make these look even better. So you can actually do quite a bit, if you can spare 11 minutes to take some photos. So the L extreme compared to the L enhance, I think you can see the contrast is a lot better. It's about, by measurement, I get about 2.5 times lower background, and thus we're getting about 2.5 times higher image contrast. The other thing about the L extreme is the color balance is just a little bit better. It's a little bit better balanced across the colors, so it's easier to get to the right color balance than the L enhance was. So both images are pretty impressive. So I guess you're probably thinking, well, if 11 minutes is pretty amazing, why do I bother with 20+ hours of exposure? Maybe I'm just crazy or something. But anyway, so a couple of points here. The red signal from hydrogen alpha is very strong, but there's some blue halo here that's really not very visible. And this is the blue-green halo is from oxygen O3, and it's just barely visible here. And it's actually quite pretty. It has a lot of detail in it, which you can't see. And if you blow the image up, you can see there's an awful lot of noise. And the problem with noise, it obscures all the detail. So from distance, it looks like we're picking up some reasonable detail. But when you zoom in, you can see that, yeah, it's really noisy. You really can't see the detail very well at all. And you could try to do some noise reduction here, but the problem is, the detail is washed out. So you're really not going to get any of that nice detail back. So, if you want a really great image, you do have to spend a lot more time than this. But again, for 11 minutes, that's not a bad accomplishment. So what I actually did is I took this a little bit further out. So now this is the Crescent Nebula with about 35 hours of exposure with the L enhance. So I had this well in progress when I got my new filter. And then, so I decided to add 8 hours of the L extreme to this. So I've got a total of 43 hours over 21 nights. So that's from May to September. As you can see, I removed the stars from this particular image here. But otherwise, I think you can see, it's impressively different and improved compared to 11 minutes. So some of the things you can see now is the blue halo is very prominent, and you can actually start seeing the detail in it. So some very nice fine detail in it that's coming out. And as well, the detail in the main nebulosity and the hydrogen alpha is a lot better. Now, actually, on the main nebula here, I didn't use any noise reduction at all. And if you blow it up, you can see there's nice detail and very, very little noise. I did apply some noise reduction to the background, obviously, because the faint nebula is still a little bit noisy in this image. But without the stars, you can see all the nebulosity really, really well. And you can see the advantage of actually taking more time to capture an image. This is actually the same image with all the stars added back in. So you can see the full impact of this really wonderful nebula. So I should say something about the Crescent Nebula. It's an interesting nebula. And actually the star that's driving it here in the center is pretty amazing. It's gone through a pretty rough history. So it's called a Wolf-Rayet star. And really what it is, it's a blue supergiant star. So it's very large. It probably has something like 15 solar masses now. And it's used up all its hydrogen. So now it's burning helium. And because of that, it burns very bright. And it also ejects gas at very high velocity. And so that gas is streaming out of the star at high velocity, and it collides with gas that the star had ejected earlier when it was in its red supergiant phase. So in that phase, it also lost maybe half its mass, or maybe not quite half its mass, but a fair amount of its mass, but in a slower process, not quite so violently as it is now. So we have all this slow-moving gas, which has been spreading out over 200 to 500,000 years, something like that. And then more recently, this star now that's burning helium and is so luminous and ejecting all this gas, that collides with the original gas, and that causes all these nice ripples here you're seeing when all those gas molecules collide. And then this star's intense UV light actually excites the oxygen, the O3, and the hydrogen gas to fluoresce, and that gives us the nice colors we see here. So this, though, is a combination of both filters. So what I've done recently is I've started capturing the elephant trunk, which is IC 1396A. It's actually part of a much larger structure. So this is actually about 10 hours using just the L extreme filter, and it's over 3 nights, about this last week or so. The hydrogen alpha here is really faint. Without a filter, you don't capture anything. I really haven't tried this target before because it's incredibly difficult. But you can see with this filter, the background is dark, and yet you're seeing a lot of great hydrogen alpha nebulosity from this. This nebula is about 2,400 light years away, and the dark part is the very dark part. It's really dark. There's nothing here. This is the darkest part of the image in the center here. It's a dark globule of cold, dense gas in the core of this structure, and then it's surrounded by hotter hydrogen gas, which is excited by the UV radiation from this very luminous blue star. Actually, there's 3 stars up here, but the central blue star is creating all the excitation of this gas that's causing it to glow. So I'm hoping there's still more faint detail to come if I can get some more clear skies. So I'm just, I guess I'm looking to Zeus, the king of all gods, as well as the sky, rain, lightning, and all nasty weather to allow me to get some more time in. Because this time of year, you know, the weather starts to get a lot worse in terms of clear skies. So I just keep my fingers crossed. So in conclusion, you know, I'm really finding the L-enhanced filter provides the majority of the light pollution blocking. So it's reducing my light pollution by about 13 times. It's really amazing for narrowband targets. And as I showed you before, it has a lot of very significant benefits for galaxies and other targets. Now, in terms of narrowband targets, the L-extreme provides even better results. 1/33 of the light pollution, 2.5 times less light pollution than the L-enhanced, and 2.5 times increased contrast, at least for these narrowband targets. And there's an easier color balance as well than the L-enhanced. There's also a review which I included on my introductory page about these filters. So it's a very good, very technical review article. And in there, he does some calculations, and he suggests that you're going to get somewhat worse performance to the L-enhanced with the L-extreme for broadband targets like galaxies. And if you look at reflection nebula, the L-extreme is really poor. The L-enhanced actually in light polluted skies is quite reasonable for reflection nebula, but the L-extreme is not. So if you want a really generally useful filter for light polluted skies and astrophotography, or to capture some of the narrowband targets, and if you only want to buy one filter, the L-enhanced is the one. But the L-extreme is much superior for narrowband targets in particular. So if you can, if you want to get the two, it's a really good deal, because the L-extreme does give you significantly more benefits than the L-enhanced in my hands so far. So any questions?
Hey, Rick, Dennis here.
Yeah.
Great presentation. I really enjoyed it. It's something I've been working on myself. One comment and one question. Comment is, what are you going to do now that we have the L ultimate? That's the comment. And the question is on your nebula that you had there, the Crescent Nebula, and you're showing the O3 regions there. In your processing, did you break apart the different bands, separate them, and do any processing specifically on the O3?
So no. So what I did, and it's probably obvious here. So I removed the stars, and then with this image, I took the main nebula, and I used Noise Exterminator, which is a new program in which can run in Photoshop, to kind of sharpen the image. I didn't really apply any noise reduction, but mainly just to sharpen it. And I have another program as well that does some sharpening. So that was treated separately, and then the background was just, the noise was reduced with more noise reduction using that program. But as far as the O3, I didn't do anything special. The one thing you can do in Photoshop is a color related saturation. So, I can tell, because the blue here is, the red here is very saturated red. If anything, you have to turn down the saturation because it just gets blown out. For the blue though, I turned up the saturation somewhat on the blue, so it brings it out a little better. But that's the only thing I did. Otherwise, it's straight out of the camera.
Right. Good job.
Yeah. I think the latest filter though is just one band, right? Not two bands.
It's two bands. So
Oh, is it two bands still?
yeah, but
Okay.
instead of the 7 nanometer that the L extreme is
Yeah.
passing, it's 3.
Yeah.
So it's even tighter.
Yeah.
So they're going for insane tightness on this thing, I guess, even to bring out more of that signal for very specific targets, right?
Yeah.
So,
Yeah.
but it's also $500 Canadian.
Yeah. And
So
I think
it's not-
I think if you look at the technical report too, at f6.3 it's not too bad, but we're starting to get in the range where you are starting to lose some signal, some efficiency. So I didn't talk about the L extreme is not quite as efficient as the L enhance in hydrogen alpha and O3. If you go to 3 nanometers, it's going to be less efficient as well.
Yeah,
So, at some point, I think it's going to be diminishing returns. I mean, this was really significant, but
the light comes in from different angles, right? And so with
that's right.
signal, the fast optical signal, those tighter narrow bandwidths are going to eliminate some of the light coming in from different angles, and you're going to lose signal.
Yeah, that's right.
So it's not recommended for fast focal ratios.
Yeah. As I said, the report that I had earlier in the presentation gives a lot of that detail and shows that data. So, and by the way, you were one of the people who convinced me to get who suggested it would be a good idea to try this filter. And there were some other people as well. And I said, if more than one person says it, I should try it. So, but yeah, I'm not sure I'm going to push it further because I think again, it's diminishing returns and diminishing funds as well.
Yeah, and I think the combination of the two filters here is a good idea because of the breadth of targets you were able to image from the backyard. All you're going to get with the ultimate is even a tighter, narrow selection of targets you want to go after. For example, if you want to get some really dim, faint nebula in only hydrogen alpha or O3, and you want to spend a gobs amount of time on it, you could go to and you're working at f6, f7, you could go to the ultimate. But that's very limited. So all right, cool.
Yeah, thanks.
Hey, thanks, Dennis. Ali, did you want to pose your question to Rick here? I know you wrote something down there.
Sure. Hi. Thanks, Rick. Just one thing. I think usually the manufacturers report those specs or profile based on the average measurements. So from sample to sample, it may not be the same exact profile, and you may get some shifts in the filtering bands. So I think to accurately compare them, I think we need to try this on a large number of samples to say, okay, this is for sure this is much better overall versus the other one. That's what
I think the difference between these two filters is really large. So I believe it. I haven't seen anybody complaining about the quality of these filters. I think they're, they do say, this these plots are not a specification. They're just an example, but I think they're pretty reasonable, and my expectations match very well this report, which looked at both filters in great detail. So I was really happy. I think I got the same results. I do, for example, for some of the solar filters, which are very narrow, I don't want to say anything because I have no experience myself, but some people complain bitterly about quality control. because the bands move all over the place and the bandwidth control is terrible. But I think with these filters, I haven't seen any complaints at all. Everyone's really happy with them. So I think you can trust that if you got one of these, it would perform well. And if it didn't, you could send it back and tell them it's not performing.
Yeah, thanks. I know I didn't have a good experience with the Optaline wideband filters. That's why.
Oh, okay. Okay, that's interesting.
Yeah, thanks for doing this experiment.
Okay, yeah, thank you, Ali. Any other questions for Rick? Yeah, that's amazing work, Rick. I mean, very impressive, and thank you for telling us about the work you're doing. That's very cool.
Thank you. I'm hoping I'm running out of filters to buy.
Is that possible?
Yeah, it is possible.
All right. Well, thanks again, and yeah, I look forward to see more of your work. That's all we have on the agenda tonight. Any comments, questions before we shut down? We've got October, November, we've got a couple of potpourris coming up. We've got a couple speaker nights coming up. We're coming to the end of the year. We're just working on finalizing Messenger this weekend. My comments in it are that we're looking for more volunteers to help out with running of the center. If you're interested in working on any of the committees, please let us know. And there'll be some changes in the council next year. We're looking for more new blood for council. So please let us know if you're interested. But it was excellent meeting, really nice variety. So I appreciate everyone, the presenters volunteering their time, and wish everyone a great weekend. And before you know it, it's going to be October, which is kind of scary, but we have our Riverwood night coming up on the 4th. So if you haven't been out to one of those, it's a great opportunity to see everyone again, because we haven't had face-to-face meetings. So we've been using the Riverwood nights to actually get caught up with everyone face-to-face. So look forward to coming out and seeing you then. So if that's all we have, I'll say thank you very much, and we'll see you at Riverwood, or we'll see you at our next meeting, which is, I believe, don't hold me to this, probably the 14th of October. So thanks everyone, and I'll put my video back on so I can wish everyone a good evening, and we'll see you soon.
Thank you.
Evening.
Night.
Night.
Bye.
Thanks.
Night.